So what you're going to have in this next section is very similar but separate from the two things you've done so far. So I'm going to repeat what you've done so far before we do the last new thing. You've been given a function or two functions, and you've been finding the area. That's what we first started with, was finding the area of a region created. That was all. It's very important you understand that area is two-dimensional and volume's 3D. It seems incredibly obvious, but when you're doing it at a much higher scale than just like the length times the width is the area of a rectangle, we're going to have, then it becomes a little bit more complicated. So remember when we were doing our area, it was two-dimensional. It was all about adding up a bunch of rectangles, right? And they all had heights and they all had widths. The heights was the distance between the two functions, right? Top minus bottom. And then our width in here all the time is what? What's our tiny little width of everything? Dx. Yep. So those were our two dimensions. It was the top minus bottom. If the bottom was 0 or the x-axis, then it was just f of x, right? So we were doing area. And then we started taking that region and revolving it around an axis that was either horizontal or vertical. And the same shape was made all the time, because you can see it with my hand when I'm revolving it like this. You're really seeing a circle, right? So those are called circular cross sections. And we called them washers or discs, depending. And those weren't about the rectangle anymore. Those were all about what shape? Those were all about a what? Cylinder. Yeah, so it's all about adding up a bunch of cylinders, but the theory behind the cylinder is that the area of its face is pi r squared, right? And its depth is dx. That volumetric model of area of a face times the depth is really what you need to understand. That with any three-dimensional solid, if I can do the area of a face and multiply it by its depth, I will get its volume. They're hard to visualize, especially there's one where it's going to be an oil spill, and its depth is going to be a function, and we will be finding the volume of the oil spill, and it's got a lot of curvature to it and functions creating it, so you just have to remember it's three-dimensional. I need to find the three dimensions. It's not like fourth grade where they're length times width times height, okay? And the reason it's length times width times height is because the area of the face is length times width, right? And the depth is the W. So it's all about, I'm going to repeat it again, it's all about area of a face times the depth. You got it? So what we're going to do today is you'll be having some function. This one's a circle up on my screen right here, and you're going to draw one of these mini chords that would slice across it. So we've always done that. We've been calling them our representative rectangles, right? But this one, they won't be rectangles. You're just going to picture going from top to bottom. And then you're going to pretend you're dropping the y-axis flat, but you really can't, because we're going to be doing them two-dimensionally. And what we'll be doing today is building up off of this solid. So we're not going to find its area. We're not going to revolve it. We're going to have it be kind of like a bread loaf pan, and we're going to bake it. All right. When I bake it, I will tell you what your slice will look like. In this case, I'm going to dish you guys up a bunch of squares. So I'll show you 4 of those pieces in there. Notice they're of varying heights, right? They're not uniform. And what we'll do is pretend you're sweeping and doing all of them. So I'm giving all the infinite chords there. I'm sweeping these squares across the circle. And what happens is a solid gets created. And it's hard to visualize the solids. So I want you to really get the math behind them. That would be hard to draw, wouldn't you agree? So we aren't going to draw them. I really need to get the visuals in there without making you draw it. So this is what the solid actually would look like if that was my loaf of bread. And then if I went and got my knife and started cutting it, I would be dishing you up a square, which seems weird because that has curvature, right? But I created it by sweeping squares. And you can see the square sliding in there so that you can see that you can get that dome and that curved dome by sliding squares across, which kind of is, I guess, paradoxical, right? It's weird. How does that happen? So they're very difficult to draw. The theory behind it, though, is very straightforward. So one last time, you're going to just watch one more time. You're going to have some figure. Rarely will it be a circle, but we are going to pretend it's down on the ground, and we're going to build up off of it. Now, it won't always be with squares. We're going to build up off of it with different shapes. That would be kind of the shape of your piece of whatever. These are dishing up a bunch of wheat thins. is really what it is. But if I were to add all of those up, because remember I told you there's a whole bunch of them in there, but if I added all of those up, wouldn't I get the volume of that dome? Right? Because technically all those squares make the dome. So what do we do when we add them all up? We integrate. So we're going to be integrating still. In your notes, where I want you to go is to the page that looks like, I got to find it here. I've got so many screens going. That guy's going, there it is, new 7. So I want you to go to the one that says volumes of solids with known cross sections. You're going to scoot past that shell method. We'll do that. We're going to do the shell method after the AP exam. We will do it, but not in that packet. And I know it says extra credit. It's not. We're just going to skip it for now. So we're going to do volumes of solids with known cross sections. I want you over here to draw this picture. They're hard to sketch. Your sketches won't look anything like the actual figures look like. So you will be given usually 2 functions, and they'll usually intersect, or it'll be the function in like the x-axis, but you'll be given a region to shade like we always have. So go ahead and grab a shader. I'll use purple on here. I want a thicker purple. All right, so go ahead and color that in. Just like before, and just like always. Should you, for your test next week, be able to find the area of this? Definitely. And that would just require 2 dimensions, no pies. If you're doing pies on the areas, you just don't get it, because the area is all about making an infinite number of rectangles. We just add up the flat rectangles, correct? But very reasonable, I'd ask you to find the area of that next week. Very reasonable, I might ask you to revolve it around the line y equals -1 and create a solid, right? Discs or washers, if I did it around this one. Washers, right? And dx or dy, if I did it along this horizontal, dx. Very reasonable, I make you go this way too. Probably not for this one, because this is more lends itself to dx. Could you tell me why? Because that's a good thing to know. Why would that purple region revolving lend itself more to a dx? Yeah, I have to switch. So if I'm doing area, I wouldn't choose to climb up the y-axis and switch. I would choose just to go top minus bottom and head on out. So today what we're going to do is lay that flat on the ground, and it's hard to picture. So we're going to pretend, we'll do one of them sort of. If you tilt your y-axis a little bit, it makes it sort of look like it's laying on the floor. So you're sort of pretending that that's on the floor, and there's actually a 3-dimensional axis coming out of it. It's called the z-axis, but you don't need to worry about that. We'll still have this same shape, but you're going to envision it laying on the floor, and we'll still build up off of it. We will just, it's going to be tricky to draw. So suppose I told you, let's start with the squares, because the squares are the easiest, and I just showed you that so you'll get a better visual. So what I'm going to do is tell you that when I bake this, and I take it out of the oven, and it's risen, and I start slicing it up, I will be giving you each a square. Will some people's square be bigger than other people's square? Yes, right? It depends on which slice you get. If you're way at the end of the loaf over here, you're going to get a very tiny little square. Let's go like right here and draw that one chord that I dropped down on that software. We are going to take and build up off of that with squares. They're kind of hard to draw well, so I'll try to do my best to give you a fairly decent one right here. So I'm going to erase that chord. So if I slant the chord a little bit, and you don't have to be good at drawing them. I hate that red on the purple. It's bothering me. Do you guys see my little, there it is. I was looking for my pen tip. Let's do the black. So you're picturing, so I did this chord. I slanted because I've tilted everything. And I'm going to take and build up off of it with squares. How many squares am I going to build? An infinite amount, okay? So the theory behind it is, if I did an infinite amount and swept them across, if I could find the area of this face, which we are going to call area as a function of x, a of x will stand for the area of the face. If I could do that, I could get the volume of the solid, because what's its depth? What do we always call this depth? Dx. So I would have one slice. So if that was a square, we would call this right here the side of the square. If that's S, then this is S, right? So what would be the area of the face? S squared, right? So that makes sense. I would just say, okay, your little wheat thin is S by S, and it's got a little bit of depth to it. So that's your wheat thin, right? It's just that this S is a function of X, really, because it's varying as I go along here. But I would just add them all up from A to B. That theoretically, that should be pretty easy to do, right? How do you think we're going to get S? How did we find this when we did area? Top minus bottom. So that top minus bottom is still going to come into play too. So that's the theory behind it. The formula just says to find the volume when you have a known cross section, so I'll put V sub cross section, it really equals the area of a face, whatever that might be. They'll be primarily geometric. Triangles, semicircles, rectangles, because those are things you know how to find the area of. With respect to X, that actually gives us our depth, and then we will integrate if it's a function of X, top to bottom to top. If it's with respect to Y, it'd be right to left. So it doesn't look very complicated, correct? It's actually not. So let's go take a look at what some people do is try to memorize it all, and that's what causes an issue. So what we'll do with all of these is I'll give you the most common cross-section shapes. So we're going to take a minute and draw this same picture on all of these. This is just my fake function picture. You can go like that. Take a minute and slap these on all of them. Slap them on there. It's actually kind of fun. It's cathartic. There we go. Feels good. It's like a what? What's it like? Okay. I'm not trying to make it look like anything. If I did so by accident, great. All right. So these are the most common. Are there 6 boxes or 8? 6. Most common 6 you'll have. I'm going to have you star the most common of the most common. The ones that generally are like on the AP exam would be the square. So go put a little AP by that. They do a lot of the isosceles with the leg across the base. So the one right below it, put AP. And they do a lot with the semicircle. So actually, I should have just said the left ones. All right, so the ones on the left are usually AP's choices. We will do all of them, just theoretically they aren't any more difficult. So for all of them, take a moment and go shade all that in. So we're going to do a little coloring for a while. So I'm not going to shade them all, but I'll do the first couple. So I'll do that one. And I'll do that one. So you guys just go shade them in lightly. Last hour, my fingertip was going with a dark, I wonder why oh, I have it on the pen. Ha! Now look at that. Sweet. Now I can shade them all. Oh. Instant. I made my fingertip thicker. How'd I do that? It's magic. I know. Now it's enjoyable when I have a fatter marker. I just have to go. Isn't this fun, Riley? I know. There we go. I want you to go to all of those and do what that software did and drop one chord down the middle. We are not going to draw them three-dimensionally. It's too difficult. So hopefully the software was good enough for you to get a visual. We're just going to drop a chord down on all of these. We will need to find the length of that chord. We are not going to call it, well, universally on all these call it S. So on all of these, drop down your chord, call it S. Drop down your chord. It doesn't matter where it is in there. Notice that S is a function of X. It's changing as the top and bottom. It's not constant, right? All right. So a couple things that are true for all of these. S is the same for all of them. It's top function minus bottom function. So let's not label all of them. Let's just do this one. The top, let's label as F, and this bottom function, let's label as G. So finding that side length is a piece of cake, top minus bottom. That makes sense, right? The other thing that's universal is throughout all of these cross-section ones, you will integrate the area of a face, whatever it might be, and then give it depth. That's model for volume universally. If I could get the area of the front of her, right, and then get the depth, I will get the volume of Cecilia. Good enough? So let's go on here, and the first one says squares. So usually your sketch is going to look like that, which really doesn't look like what the solid will look like, but you'll just pop a square out on there, and you'll do this. And you'll realize that that's one piece of the infinite amount that you're going to be dishing up. You're going to look at it and say, well, I know how to get the area of that face. I do side times side. That's the area of the face. What's the depth? Dx. That's one slice, and it depends on where it was, how big the slice is. And then I would integrate from the intersection to the intersection. How do you think we'll find those intersections? Depends. Calculator active, calc intersect. Non-calculator active, set equal and solve, and it'll factor and it'll be nice. We're used to that too. So a lot of old math with a new concept. So that's it. What about if it's a rectangle? Well, let's go shoot this up off like this. It depends. They have to give me more information then. They can't just say a rectangle. Doesn't it depend on how high I make it? Right? So they'll tell you. They'll either say it's constant, like they'll say the height of the rectangles is 4, in which case everybody would get a cracker of the same height. Agreed? Or they might say it's 4 times the base length. It just depends. They'll have to tell you though. So there'll be some information given about the height of your cracker. So let's go take a look. How would I get the area of the face? Well, I'd still have on this one, it'd be 4s times s, so there'd still be that s squared in there. I'd integrate from a to b dx, right? But I'd have a 4 out front because constants come out front. Or, had this been constantly 4, so put this so you know we're doing the 4 or the 4s. It depends. If it was just a 4, what would go in the integrand? Well, the 4 times the s. So do they all have, somebody last hour said, do they all have an s squared in them? And my answer was most. But you got to watch the problem, because if it's 4 times the side length, yes, it has an s squared in it. If it's just constantly 4, then it's s dx. So I can't tell you that they all have an s squared in them, but I can tell you that most do. So now what we'll do is change the shape. We aren't going to deal with a quadrilateral. We're going to pop some isosceles right triangles up out of those. Remember, isosceles have sides of the same length. And if they tell you that one of these legs is across the base, you'll notice that for an isosceles, so what would it look like this, and that would have been S, and that would have been S. Well, how do you get the area of a triangle? 1/2 base times height. Or it's half of the square that it sits in. But this one, if I did the area of the face, I would say 1/2 of side times side. So I'd have a half out front. We're going to be calling that the multiplier. You'll have them memorized fairly quickly. But for the isosceles with a leg across the base, it's just like the square. So it doesn't really need to be memorized. It's just half of a square. Are you good with that, Ashley? That makes sense. And how do I find S again? Top minus bottom. How do I integrate? Don't ask me that, right? We better know how to integrate by now. If the hypotenuse is across the base, that's a little different. Because for my isosceles triangle, I'd be putting the longest side across the base. So it's not going to pop up as high. So do you think I'll have less volume or more volume? What does your gut tell you? Less. I'll visually show you how much less it is, and then I'll mathematically show you. So this scenario is splitting it into 2, but when this is the hypotenuse across the base, then if you take a look, when I throw this hypotenuse across the base, how many triangles does it take to make the rectangle? 4 of them, or the square. So you can intuition would tell you that would be a 4th, but I don't like intuition. I do like intuition, but I also like mathematical soundness. So let me show you why that works. It goes back to, by the way, it'd look like this then, right? It'd be popping out that way. So let's see who remembers some of their Algebra 2. In Algebra 2, if this is 7 and that was 7, what was the hypotenuse? Excellent. 45, 45 relationships. So if the hypotenuse is known, how do you get back to that side length? Divide by root 2. That makes sense. So if my hypotenuse is S, And you don't need to understand these proofs, but it's nice if you do. It means you know more than you ought to. For me to go and get this base and the height of the rectangle, I'd have to do s divided by root 2. That makes sense, I think. Do you think so? Okay, so how do you get the area of a triangle? I do 1/2 of its base times its height. And for right triangles, those are these two. So if I did that, don't write this in your notes. I don't want your notes being messed up with this. I do 1/2 of the base times the height. Watch when you clean that up. You get the s squared and what ends up being on the bottom. 1/4. So I showed you with the visual, and then also we got the math backing it up. So you just need to know that when the leg's across, it's a 1/2. When the hypotenuse is across, it's a 1/4. Kind of need to just memorize it because you don't want to have to create it all the time. Very common is to build a semicircle up. Again, I'll derive that one for you, but you're going to want to commit this one to memory so you're not always trying to derive something that's going to happen every time. So we'll still call that S. Now see how bad the pictures look, but this one kind of makes sense with the bread thing because it is kind of like a baguette or a French loaf where it's flat on the bottom, right? But when I dish it up, you get kind of that semicircular shape. So my question is, I still need to do the area of this face. Well, how would I do the area of a 1/2 a circle? If it was geometry class, right, I'd do 1/2, and this one I would like you to write down so you can see where this one comes from. You'd do 1/2 pi r squared. In this scenario, though, what would be the radius of that circle? 1/2 s. Yeah, so if I go replace this guy with a 1/2 of s, watch what happens. I'd have 1/2 pi. Come on, marker. It's saying stop doing math. I'm sick of it today. That's my marker talking. Well, when you clean that up, what's in it for sure? Pi. Agreed? What's the remaining fraction? 1/8. So the multiplier that comes out front, and again, this was a 1/2 s, sorry. The multiplier that comes out front is pi eighths. So again, you're going to integrate side squared, but you'll have a pi eighths out front. That's easy. And the last one, the equilateral triangle, I've never seen this on the AP, but that doesn't mean it won't ever. But in all the zillions of practice tests I've given, there's never been equilateral triangle. So you'll commit, and I won't put it on my test either. But just in case, I'm going to tell you what that one is too. So let's pop this guy out. I could derive it, but I'm not going to. I derived 2 of them. That's good, right? You're fine with that? I'm just going to tell you. It ends up having a multiplier out front of the root 3/4. So what usually happens when this one pops up in Calc 2 is the kids say, I know it's either root 4/3 or root 3/4, and I just say, think about it. What would end that debate for you in your brain? Because you're going to know it's about 3s and 4s, and you're going to forget where they go, so you're going to go, which one is it? What should end the debate? If it was root 4/3, what would it look like? 2/3. So just remember it has the 3 and the 4s, and it's the one that wouldn't simplify. You won't see this one outside of the worksheet. I won't put that one on the test. No test. The other ones are fair game. All right, so again, for all of them, remember that your side length is top minus bottom, or if it's a dy problem, right minus left. These tend to be primarily dx, which is nice. This is easier than revolving solids, actually. And for all of them, one of the dimensions is always dx. What's in most of the integrands? S squared. Not always, but in a lot of them. All right, we'll just go do it and quit when we're done. So again, here's some shapes that I'm not going to make you draw, but you could see it. This would have been one where it says with rectangular cross sections, and they would have said with the height maybe twice the base or something. This would have been a semicircular one, looks kind of like an igloo, and what would this guy have been? If I cut it, equilateral triangle cracker. What would that be? Or Triscuits? No, those are squares. Triangle Triscuit. All right, that's what that is. If you were to cut it. We're not going to do this one right now, so mosey ahead to this. You might say, oh my God, we're going to do all these. It's going to take forever. It won't, because I'm only going to do the new stuff, which means I'm only going to set them up, because if Rachel can't integrate right now, she should have taken care of that a long time ago, right? So we're not going to integrate them, we'll set them up. Here's what we need. We're going to have the same loaf pan for all of them. What's it going to look like? It'll have one function being x plus 1. So it'll be a linear function, it'll be rigid. And then x squared minus 1, which is my parabola that opens up. So shade in the common region like this. This is the bottom. I mean, it's a funky loaf pan, but that's what it is. And then I pour the stuff in and I bake it and it rises, and then it rises in different ways. It's going to make all these different shapes. How would I find the volume of the entire loaf? It's going to depend on how I cut it and how I bake it. But for all of them, all right, S of x for all of these, we'll just call S, but it is a function, right? Short here, it's longer here. And we'll talk about where it's at its most in just a minute. How would I get S always? It's easy, top minus bottom. That's nothing new. Make sure you grab the correct one. It'd be x plus 1 minus, don't forget the parentheses, but that's nice and easy on a little cleanup of it. My pen is being naughty. No, mad at it. All right, it would be negative x squared plus x plus 1. Did I make any sign errors or am I good? Step back. Plus 2, thank you. That's where I make mistakes all the time, at the silliest places, which is good. It's better than making a big mistake, but I always do that. All right, so that's my S. What if I were to ask you, I'm going to ask a deeper level thought. Suppose this is an AP test, and part A was find the area, that stuff. You're like, I'm good, right? That'd be easy. And then part B was revolve it around the x-axis, and you're like, I can do that. Right? And then part C was to build up off of it with squares. We'll do that in a second. But part D says, when is S at a maximum? Which means when do I slice it? And if you get that slice, yours is the biggest. What would you do? How do you find where functions reach their maxes? What do? We take a derivative. And what do we set it equal to? It's either at the endpoints or where the derivative equals 0, but the endpoints are ridiculous on this one. You obviously get a very tiny piece if I'm giving it to you, right? So that's not going to supply me with any volume. So it's obviously at a turning point. So if I really wanted to know where to slice this to give you the biggest slice, because I like you the best, so you get it when I slice it at x equal to, where did this come from? That's the derivative of S of x. It's S prime or ds dx. It's the side changing as x changes. So it's all that rates of change. I'm trying to find where that's the fastest. I would slice it at x equals 1/2. That makes sense because this is all the way over at 2 and it is right over here somewhere. Doesn't it look good? Right? You would get the maximum slice the minute my knife hit a half. That's a great question. I would love to ask you that one a lot on the worksheet, but I don't. Most of them are just finding the volumes. All right, let's go do that. For all, we need intersection points. This one's entirely obvious at -1, 0. What does the other one look like it's at? 2, I'd go with common sense and could do a little check on 2, and 2, 3 is for sure definitively the other intersection point, but you could factor, find it, you'd be good. You're good at that. All right, for the setups of these, it's nice and easy. It's all about the volume being the area of a face and then times depth, and I integrate. So I don't need to memorize everything. For the squares, that would be me popping up a square right here. How do I get the area of a face? I do side times side. Go label that, by the way. Make sure you understand that this right here is the S. All right. dx. And I'd integrate from where to where? -1 to 2. Where would I get S from? It's right here. It's the same for all of them, so we'll just dump it in. I am not going to square that, and I am not going to integrate it. That's why these are going to go fast. All right, the next one. If it says rectangles with a height of 2, you set up what you think you would need. You don't really need to memorize formulas. You need to get the area of a face and then give it its depth. Should be done already. Right, Afnan? Right? If I have rectangles that have a height of 2 and a side length of S, what's the area of this face? 2S. I will integrate 2S. What's its depth? dx. There's your, by the way, you always need 3 dimensions. 1, 2, 3. 1, 2, 3. Integrate from -1 up to 2. What if the rectangle is 5 times its base? Then gone is the 2, and in comes a what? 5s. How do I integrate that? It would be 1 dimension, 5s, times the next dimension, s, times the third dimension, dx. I pull the constant out front. Am I memorizing? Not at all. So far right now I've just created them because it's all about area. So that would be s squared in there. So do they all have an s squared in them? No, but the majority do. All right, quarter circles we won't do. Semicircles, though, that one I did say to memorize. It had the s squared in it. It had the dx. What was its multiplier? Circle pi, and then you just need to remember that it was pi eighths. You need, or for the group test, you better hope somebody remembers that it's pi eighths, but it's pi eighths, right? Let's do the next one. For the isosceles right triangle, it depends on whether the legs across the base or the hypotenuse is across the base. Okay, so if the legs across the base, we have a multiplier of 1/2, and this says base is short leg. So if, by the way, if you have a hard time visualizing that one, man, my picture's getting super messy, but I'm not going to bail on it. I'm going to grab, just a second, I'm going to grab yellow so you can see it. This would be, what the heck? And I didn't swear, and it's being recorded. I'm proud of myself. What? No. Yeah, there we go. All right, so if I built up off of it, oh, that felt good. If that was a leg and this was a leg, you can see that it's half the square it would have sat in. So that's the bigger scenario. What multiplier does that one have out front? That's really all I was trying to show you with the yellow. It would have a half. What if I said, or is that coming up? Oh, the next one. What if I said that the hypotenuse was across the base? That shortens it. It makes it less, so you just have to remember the other fraction. What's the other one? You'll write that out front. Okay. Equilateral triangles require a different multiplier out front. You do need to remember that has to do with the 4s and the 3s. What's the multiplier for the equilateral triangle? With 3/4, integrate s squared dx. All right, so last up. How might these appear in a whole different context? Here we go. Not that one. And then I will quit right here. That's as far as I got in the other class, too. So tomorrow when you come in, I'll do one more and let you work. And you already have the packet, right? And it'll be due on Tuesday when you come in. So tomorrow's almost all a work day. You can get in groups like you did yesterday and work it out. You should finish most of it. So this is an entirely different problem. First of all, it's calculator active, so take out your calculators. And I know it's a pain and you don't like to, but if you don't practice the entries and then you come up to me and say, I don't know how to do this on the Inspire or on the, I won't tell you. Okay, you need to work it out long before a test. So you should be entering them. Physics people, make sure you check your mode because this is tricky. So make sure you're not still in degree mode. That causes huge issues. All right. So when you're given a calculator active, one best thing to do is enter this in Y1, enter this in Y2. Look at the nature of the functions that you're graphing. I would go immediately and hit my window. Or, because this is Triggy, there's a zoom button that's nice for trig ones, but zoom 7, but I wouldn't do that because it'll give you all the stuff over here as well. It goes from -2 pi to 2 pi. So I would just manually take your window. It looks like 1, 2, 3. I would set my window to go from 0 to 4 by 1s on the x-axis. I would also notice that they're both sine functions, and those are bound by 1 and -1. So I would set my y's just to go from -1 to 1 by 1, and you'll get a really nice picture of that oil spill on your calculator. That's what I'd suggest. I'm going to wait for you guys to graph it. So now we've got this region R is represented by the surface visual. So you're looking down from an airplane. Okay, you're looking down at the ocean, you see an oil spill. You're looking at the surface area of the oil spill. Go shade it in. And if this was AP and I asked you for the surface area of the oil spill, that should be a pretty easy thing to figure out. Let's talk about that because I don't like you to get like tunnel vision. Yes, we're talking about cross-sectional volume, but could I ask you in part A to find the area of that oil spill? Yes. Top function minus bottom function dx. Why no pi's? Yeah, it's not a volume. I'm not revolving it. It has nothing to do with that. All right, for all of the questions, though, you need these. How do you get these? You need your constraints on the oil spill, right? How do you find them? Because it's calculator active, calc intersect. And again, if it's not, get it equal to 0, it will factor. So I need one side of the room. Let's do this side over here. If you guys could get me the right one, because everyone always does the left one first and then we have to wait. So you guys do the right side only, and if you guys can do the left. And we're going to take it, I'm not going to bother to store them today. We're just going to write them down. Thank you. I'm going to steal that. So we've got point over here. You could call it A equals if you want to just write that down one time. That's often recommended. You could even store it in A, but remember, if you're going to use a variable, you have to define it. So somebody on the other side of the room, could you give me, over here, I'll call it B, and I'll write B equals, and I don't have to write it again. Anyone have it on this side? I'm going to steal it. 3.4034. Did anyone get it more decimal places? I'd like it to be more accurate. 3. All right. If this were a 4 or 5 part question, I would take the time to store them on your calculator, but we're just going to do one question. But if I did have to do area and then revolve it and then build up off of it, I would store them. Is it wrong? Oh, okay. 3.043. 4. Is there still 4? 3, 9. No, now I'm catching. No, whatever. You guys write it down. I don't care. At this point, I don't even care. All right. It's 3 point something. All right. So now, so this is the oil spill, right? And that's pretty applicable. So I've kind of done a math model for the oil spill. Probably is not exact, but I've confined it as much as I could with these math models. Then what I know is it doesn't have uniform depth, and I fit a function to the depth of the oil spill. It probably realistically is a little bit deeper in the middle, right? So the depth, so again, you're looking down at it, but let's suppose that represents the depth function. It's fake, right? But you're again looking down at it from an airplane. And you're going to picture that it is like a three-dimensional solid that you're going to slice. Yes, it's liquid, so that's weird. But you have to picture that you're going to go in there and take a slice of the oil spill, and you have to know that that oil spill has 3 dimensions. And that's what needs to go in your integrand. All 3 dimensions of the oil spill, right? One of them is always dx, right? It's the thickness of that slice that I'm going to take. So you're picturing me heading in there with some sort of a knife that miraculously can cut water and make it solid. Right? So it's going in there, it's slicing it, and it's going to go all the way down to this part of the depth function, and I'm going to have what's called a cross section. You're going to be doing one with a river. It's going to be about the volumetric flow at a dam on a river. And you're going to picture slicing through. So it's really hard to visualize. But one dimension is dx. You need to supply the other dimensions. I know I'm going to integrate from A to B. I know I'm not revolving it, so no pi's. And these aren't semicircles, so no pi's. These are weirdly shaped things. They're not squares or rectangles or triangles, but they still have 3 dimensions. So somebody give me one dimension of the slice. I gave you one, dx. I need another dimension. F of x is just the top function. It's not a dimension of my slice. F of x what? Minus g of x will give me one of the dimensions of the slice. It'll give me, for lack of a better term, the length of the slice, right? So why can I call it f of x minus g of x? because they did. Now, if you call it y1 minus y2, you better define it somewhere so you cover your butt on that. But, okay, now I have 2 dimensions. You might say there's 3. No, I have 3 things written, but I have 2 dimensions. I have a length and I have a thickness. What's my 3rd dimension? The depth. Yeah, do you see it? It's so hard for me to draw them. I'm really doing my best to try to, this is a very difficult concept. I'm really trying to, are we good? You're quiet because I have the headset on, but I feel good, like you're making eye contact. There's a couple deer in the headlights, but not many. So how would I evaluate this? I'd math 9, but keep in mind, had I done this and this was like part D, I probably have these stored in some letters, my favorite ones. I probably have this stored in Y1 and this in Y2, so how would I bring them in? How would you bring them in? Use your VARs, but if somebody could go ahead and give me an answer to this, I think from last hour, I think this is the one that's 4 point something, so if you're getting that, I could be wrong because I've done a lot of math today, but I'm pretty sure. So go math 9 it. Accurate to a minimum of 3 decimal places. And I'm going to turn this off because I'm sick of it. I hate using this. Oops, it's still on. Oh, sorry, Annika. You're the reason I'm using it. And I said I hate it. I don't hate you, honey. You're super.